Hi, everyone. Welcome back. I hope you had a nice lunch and a refreshing break from mathematics. Some of you didn't take a break from mathematics. Good for you. Our next speaker is Pramod Achar, and he's going to tell us about cleanness in Springer theory.
Okay, thank you very much. It's an honor to have been asked to speak at this conference in celebration of Dan Nakano. He's had a big influence on my career over the years. He's supported me in various professional contexts, and there have been a lot of links between UGA and LSU over the years. I think among my students, one was an undergrad here, two were postdocs here, one is a professor here. And I think all of my students have been to UGA for either a Southeast Lee Theory meeting or a summer school. And I think it's hard to overstate the impact that Dan has had in the region with his leadership in the Southeast Lee Theory workshop series, and just his the drive he brings to getting junior researchers engaged. And I think almost everyone in this room has benefited from Dan's efforts in this regard. I want to say a little bit about mathematics as well. So I haven't collaborated with Dan directly on math, but I have made use of his mathematical knowledge. So I want to mention some work with Will Hardesty. This is not the main topic of my talk, but Will Hardesty was a student of Dan who graduated in 2016. I think he was mentioned in a couple of other talks. And after that, he came to LSU as a postdoc. And I think this was a really great match for both of us in terms of how the different things we had expertise on meshed together. This first paper here, oops, there. Okay, this first paper here is called Calculations with Graded Perverse Coherent Sheaves. So before we read this paper, I thought of myself as someone who, I knew something about perverse coherent sheaves. I knew about their theory. I thought I had some intuition for how they worked. But in fact, I've never done any really explicit computations beyond SL2. And in fact, it turns out I was not able to. This paper is basically about PGL3. And what Will brought to this project was a profound knowledge of group cohomology, of line bundle cohomology. I mean, knowledge that he gained from Dan while he was a student here. So he brought knowledge about what's true, what kinds of tools there are to do computations, and something that's a bit more subtle, he brought intuition about what kinds of things to expect. And when we were writing this paper, I argued with him a lot because I thought, I had intuition from the SL2 case, and I was wrong about just about everything. And writing this paper really opened my eyes to how badly wrong my expectations were. And I think this paper owes substantial intellectual debt to Dan. And after we wrote this paper, I sort of, my eyes were open to how different perverse coherent sheaves are from what I thought. And Will's thesis was about something called the Humphreys conjecture for SLN. And when he came to LSU, we started trying to prove it for other groups. And we proved it in a paper with Simon-Riche for large characteristic. But I think this paper led the way to this other paper in which we proved part of the Humphreys conjecture, the relative part, as soon as P is bigger than the Coxeter number. And I think the kinds of things that Dan is really an expert on when it comes to, things like line bundle cohomology, they play a really important role in the arguments in both of these papers. So anyway, I think I'm indebted to Dan both career-wise and mathematically, and so I want to express my gratitude and also say happy birthday. So the main part of the talk, the work that I want to talk about, it's not this work with Will, but it is work that started with so it's joint with Chatterjee. She was here earlier in the week, and she had to leave early. And she was a postdoc here, and this work, most of it took place while she was at UGA. So I'm going to start with an example. And the example involves the nilpotent cone for SL2. So this is going to be something really concrete. I'm going to do a kind of elementary algebraic topology calculation. So if you have 2x2 matrices, nilpotent means, of course, some power over the matrix is 0. And for 2x2, this comes down to saying the trace is 0. So that is encoded right here by, I've already put in a minus sign here. It means the trace is 0 and the determinant is 0. So this equation says the determinant is 0. And this is kind of a picture that can give you some intuition. This is basically the graph of this equation in R3. Of course, I didn't write C anywhere on here. Oops. Sorry. Okay. Yeah. So basically, nilpotent 2x2 complex matrices. So there's a 0 matrix, so that's the cone point of the cone, and the rest of it is the set of nilpotent matrices whose Jordan form is this. So it's the conjugacy class of this matrix. So when you draw the real points, it looks like it's disconnected, but the complex version is connected. And in fact, you can write down a really explicit covering map. So there's a map from C2 with the origin deleted. So this thing is called C reg because, yeah, so I guess C stands for class and reg stands for regular. So this is the regular nilpotent orbit. A tiny little exercise you can do is to check that that this map here is a 2-to-1 covering map. So I think well, yeah. Anyway, I think it's very easy to see that the preimage of each point has 2 points, and then you have to check that it's surjective. Sorry, was there a question? Okay. So there's the 2-to-1 covering map, and this thing, C2 minus 0, so that's, of course, the same as R4 minus 0. And this is homotopy equivalent to S3, which is simply connected. So this is, in fact, the universal cover of C reg. And so something that you can deduce from that is that the fundamental group of C reg is the group of order 2. And once you know the fundamental group, then you can start talking about local systems. So, so I know that not everyone in this audience is thinking about sheaves and local systems every day, but the only thing you need to know here is that a local system, well, it's a kind of sheaf, but specifying a local system is exactly the same thing as specifying a representation of the fundamental group. And if I stick the word irreducible on here, then I can stick the word irreducible on the other side. And so now that we know the fundamental group of C reg, we know how many irreducible local systems there are. So there are 2 irreducible local systems on C reg, and they're the trivial and the sign. So the trivial I'm going to write as Q underline, so it's the constant sheaf with value Q, and the other I'm just going to write as SGN. Okay, so now I want to pose a problem. So this is the same picture from the previous slide. So I've got C reg here, I've got 0 here. And the question is this. So suppose I take a local system on C reg and I push it forward along this inclusion map. And I want to understand what happens at the origin. So I want to compute a stalk at the origin. And there are various techniques for doing this. And a trick here is so trick is that because the variety we're looking at, so because this nilpotent cone has a contracting, there's an action of C star on it that contracts it to a point. Contracting action of C star. There's a kind of trick to computing this stalk, and the trick is this: pushing forward and taking the stalk at 0 is the same as taking sheaf cohomology of C reg with coefficients in L. Okay, so well, that changes one problem that you maybe don't know how to do into a different problem that you don't know how to do. But but this thing we can try to tackle using covering space theory. So let's use the covering space from the previous slide. So we had this map that I called F on the previous slide, which was a 2-to-1 covering map. And when you push forward the constant sheaf along a covering map, you get, well, if this were not the universal cover, this would be something like inducing a representation from one fundamental group to another. In this case, you're inducing the trivial representation from the trivial group to Z mod 2, and so you get the regular representation of Z mod 2. So that means you get the constant sheaf, direct sum with the sign sheaf. So this is the local system corresponding to the regular local system. Yeah, I guess the word regular is playing two different and basically unrelated roles in this sentence. Okay, so now that you've got this direct sum, then we can take sheaf cohomology on both sides. So so that means that H C reg comma F star Q, this equals H C reg Q direct sum H C reg and the sign representation. And all of these things can get simplified a bit. So this when you push forward and then take hypercohomology, that's the same as taking cohomology of the original thing. So that's, this is C2 minus 0 Q. Okay, so now there are some things that we actually know. So C2, remember that this is homotopy equivalent to the 3-sphere. And this is the 2-to-1 covering map. So does anyone in the audience want to call out what topological space you should think of here? Oh, it's RP3. Okay, so this is the cohomology of the 3-sphere with Q coefficients, and this is the cohomology of RP3 with Q coefficients. And now, if you remember, I think probably everyone remembers that the cohomology of S3 is, it's one-dimensional degree 0 and 3, and it's 0 otherwise. RP3 is a little bit funnier, but with Q coefficients, it turns out that has the same cohomology as S3. So this, let's see, so this thing equals this thing, but the right-hand side is supposed to be direct sum, and so therefore we conclude that that this is 0. So here's the conclusion. So J star of the sign local system and then stalk at 0 is 0. And I'm going to write this another way. There's if you take a sheaf on a subset and you want to make it a sheaf on the bigger space, which is 0 stalks outside where you start with, that's called the extension by 0 functor, and that's written as J exclamation point, which is usually called J shriek. So what we just finished doing on this page is showing that the sign local system has this property that it's pushed forward. Oh, actually, let me modify this slightly. What I've written here is true, but I want to just take off this stop part. J star sign equal J shriek sign equals J star sign. So this is the conclusion. Okay. So yeah, the upshot is that this looked like something hard, but it so, some years ago the story is not relevant to anything, but I was subbing for a colleague of mine teaching differential equations, and I wanted someone in the class to tell me we were learning about class transform, and we're reviewing properties, and someone said it's linear. And I was like, okay, can someone tell me what linear means? And there's silence, and finally one person back goes, "It's zero." But that was really disheartening. But then I went and complained to my colleague, and he's like, "Well, I told them that if a math professor asks you a question and you don't know the answer, it's often zero." So this is zero. Okay. So that was the warm up. So part two is cleanness. So here's the setup. So now I want G to be a reductive group over the complex numbers. N is the nilpotent cone in the Lie algebra. So we saw this in one of the earlier talks today. C is going to be a G orbit in N. So one thing to keep in mind is that there are always only finitely many of these. In GLN, they're classified by partitions of N. There are finitely many. And then L is an irreducible local system on C. So another thing to remember here is that it turns out the fundamental groups of these orbits are also always finite groups. So there's only finitely many irreducible local systems on each orbit.
But you take into the rational numbers.
Yeah, for now I'm taking over the rational numbers, yeah. Okay, yeah, an irreducible, yeah, an irreducible Q local system. Okay, so the definition, so the first word in the title of my talk is cleanness, and what clean means is exactly this, that the push forward is the extension by zero. So it's exactly the phenomenon we saw in this example of the sign local system for SL2. And so there's it's convenient to be able to be a little bit loose with the language. So you could say the local system is clean. That's the way it is inside this box. Sometimes there's this more complicated notation that's called IC of CL. I mean, you might say that whole thing is clean. Well, don't worry about what that is for now. It's just some notation that tells you the orbit and the local system. Okay, yeah. So the main things I want to comment on this right now is that for SL2, the sign local system on C reg is clean. So I've said that already. For other groups, oops, sorry. For other groups, a point I want to emphasize over the course of the talk is that cleanness is rare. We're kind of lucky that there is an example on SL2. Like if the smallest example had been on SL25 or something, I wouldn't have been able to do a computation at the beginning of the talk. Cleanness is rare, and it's crucial for Lusztig's theory of character sheaves. And I want to explain this connection a little bit, and I need a supplemental notion. So the next thing I want to define is the notion of cuspidal. Yeah, so well, now we can't avoid getting more into sheaves and perverse sheaves and derived categories of sheaves and stuff. So the setup is this. So if you have a parabolic subgroup and a Levy subgroup, then I want to look at these categories. So this category right here, DBG of G, that means the derived category of G equivariant sheaves on G, and this is the analogous thing for the Levy subgroup. And there are some functors that go back and forth, which are called, parabolic induction and restriction. So this is called induction. Oops. There. Well, anyway, it's okay. The color is not constant. This is restriction. And let me mention a couple of properties.
The conjugation, right?
For the conjugation action, yeah, that's right. Yeah. So the question was for the equivariant derived category, equivariant with respect to what? And the answer is for the action of G on itself by conjugation. Okay, so one property is that both functors send character sheaves to character sheaves. Another feature that they both have in common is that they both send perverse sheaves on the nilpotent cone. If you have a perverse sheaf support on the nilpotent cone of L, then the induction functor sends it to something that lives on the nilpotent cone of G, and vice versa. So I guess I shouldn't write T2 here. I should write arrows in both directions.
Did you switch from the group to the Lie algebra?
Yeah, that's a good question. Yeah, so the question is, did I switch from the group to the Lie algebra? So the way you make sense of this is that the nilpotent cone of G is isomorphic to the variety of unipotent elements in the group.
But large characteristic, not for very small.
My groups are really complex numbers. So zero counts as large characteristic. If you're looking strictly at perverse sheaves on the nilpotent cone or the unipotent variety, they're isomorphic with a G equivariant isomorphism. So there's literally no difference between them. For character sheaves more broadly, working on the group is different from working on the Lie algebra. And I wanted to say it on the group setting because I really want to mention things that Lusztig proved way back in the mid 80s. And in some cases, the Lie algebra analogs of these are true, but not proved until more recently. So so that's why I'm stating this part in the group setting. And then the main definition I want on this page is the word cuspidal. And cuspidal shows up in various other places in mathematics and even in representation theory. And the meaning of cuspidal is something you can't get from a smaller group. And so there are two equivalent ways to say it. So a perverse sheaf is called cuspidal I wrote if it doesn't arise by, and so you have to be careful about what you mean by arise by. It means if it's not a direct sum end of, or if it's not a quotient of something you get by an induction functor from a proper parabolic subgroup. And it turns out that's equivalent to requiring that every restriction functor send it to 0. So that's what cuspidal means. Okay, so here's how these things fit together. So this is part of the so in 1985, 1986, Lusztig published a series of 5 papers inventing the theory of character sheaves. And part of what he proved in that, he proved that every cuspidal perverse sheaf is clean. And this cleanness statement is crucial to classifying character sheaves. And then these 3 statements together, I left a gap here because these 3 kind of go together. These 3, so the third one is, the third one says that character sheaves, like if you take a stalk of a character sheaf at 0 and odd degrees, it's that type of statement. And it turns out these 3 he has to prove together by simultaneous induction on the rank. So the pattern of the proof is that if you already know for all lower rank groups that the cuspidal things are clean and you've classified the character sheaves and you know this parity vanishing property, then you can go up and prove that the next cuspidal you get to is again clean. So this is proved by simultaneous induction on rank of G. After that, then you get some consequences. So most perverse sheaves on the nilpotent cone are not literally character sheaves, but you get a parity vanishing property for them as well. And then at the very end of character sheaves 5, Lusztig gives a procedure for computing stalks of perverse sheaves on the nilpotent cone. And this is something you can implement on a computer. It's often called the Lusztig-Chatterjee algorithm. Well, I guess a special case of it had been discovered previously by Chatterjee. And the Lusztig-Chatterjee algorithm is kind of step 0 in the project of computing characters of finite groups of Lie type by an algorithm. So it's the very beginning of that process. So this is something that ultimately is of substantial importance to the representation theory of finite groups of Lie type.
You said that without the rank, you mean semi-simple rank.
Semi-simple rank, yeah. Oops. And then it's kind of a correlate. Like after you're done proving all this, you prove that every cuspidal is clean. You classify the characters used, and you have this algorithm for computing stalks. And you can see from the algorithm that things that are not clean, not cuspidal, are never clean. So that's at the very end. So then we find out that on the nilpotent cone, clean and cuspidal are actually equivalent. And I told you earlier that this is rare. So let me tell you how rare it is. How rare is it? So for the symplectic group, for sp2n, there exists a unique cuspidal ICCL, so a unique orbit and local system on it if n is a triangular number, so 1, 3, 6, 10, etc., and no cuspidal otherwise. And to emphasize the rarity of this, so when you get up to so if n equals 10, you're on sp20. So the number of nilpotent orbits is approximately something like the number of partitions of 20. So you can see that, I mean, that's a number that grows very fast. But there's only one cuspidal there. When you go to sp11, there are no cuspidals. And so no clean local systems. Before I go on to the next part of the talk, I want to do a little bit of a digression. So yeah, up until now, my groups have been over the complex numbers. But most of this stuff makes sense for groups over other fields. You have to be a little bit careful because the geometry of the nilpotent cone or the unipotent variety is a little bit different when P is small. So what happens is that you get more nilpotent orbits. So Lusztig conjectured way back in 1985 that this theorem that cuspidal implies clean remains true in these low characteristic cases. And this is a theorem now. I'll tell you what the attributions are. So yes.
In characteristic theorem complex case, what's the new character sheet?
Character sheaves are defined I mean, character sheaves are defined over the complex numbers. You can't take trace of Frobenius, but the notion of character sheaf is valid over the complex numbers. So, and the the ingredients in the classification are kind of independent of the field. Okay, so classical groups in characteristic 2 and E6 in characteristic 3 and E7 in characteristic 2. These were done by Lusztig in his original paper on character sheaves. So this is Lusztig, 1986. Then a few more cases. So these cases and these cases were done by Shoji in 1995. And then two more. So E6 in characteristic 2 and E7 in characteristic 3. These were done by Ostrich in 2003. and there are two left, and those were done by Lusztig again in 2011. And I saw Lusztig give a talk about this in 2011. It was at the birthday conference for Jean-Michel and François Digne, and it was a really fun talk because it was clearly a problem that he'd been wanting to solve for 25 years, and it was finally solved. And it turns out that every one of these papers introduced a new argument that covered a few more cases but didn't subsume the previous ones. So still currently you need all four of these papers to have the theorem in general. So who knows if someday there'll be just a direct proof that does everything all at once. But for now, this is the situation.
So taking the local system over the same field.
So these are for characteristic zero local systems. So like the group could be over FP bar, but you'll take QL local systems. So characteristic zero local systems.
So you are taking QL local systems.
Yeah. So far up in this talk, I've been taking characteristic zero local systems, and I'm about to change that. Okay. So yeah. So part 3 is modular cleanness. Okay. Yeah. So the setup so far in the talk has been that I take my group and my nilpotent variety over the complex numbers, and I take sheaves of Q vector spaces, or I mean, whatever your favorite field of characteristic zero is. And now I'm going to change, and for the rest of the talk, the varieties remain over the complex numbers, but I'm going to take sheaves of vector spaces in a field of positive characteristic. And I wrote FL bar. It doesn't have to be FL bar. You can take a non-algebraically closed field, and it doesn't matter too much unless it gets very small. And then, like, you know, if you end up like if your field is so small that it's not a splitting field for some fundamental group, then it's different. But let's just take it to be algebraically closed just to be safe. So the context is that in the past 15 years or so, there's been an enormous burst of activity with sheaf theory with coefficients and positive characteristic. I mean, new tools appeared on the scene, especially these so-called parity sheaves about 15 years ago. And there's just been a lot of activity since then that, you know, if you go back to the 80s, papers in geometric representation that use perverse sheaves somehow, the perverse sheaves are always with characteristic zero coefficients by default because that's where the powerful tools were. And so with the advent of these new tools, we've seen things like, I think that probably I mean, one of the most notable achievements is the proof of the tilting character formula using the p-canonical basis. Maybe I'll mention some of the other things that are in this vein, like the I think the Humphreys conjecture that I mentioned at the very beginning of the talk, that involved input from these positive characteristic sheaf theory methods. There's something called the Mirkovich-Volonin conjecture, which was due to myself and Laura Ryder. There's the Finkelberg-Mirkovich conjecture, which is a theorem as of like I think they posted that. Well, this is Bezrukavnikov, Risch. So, well, it's a series of papers and Ryder is part of that series. I think this was posted like a month ago or something. There's other work of Risch Williamson on geometric approaches to the linkage principle and all kinds of things. So there's been a lot of activity. And so this is kind of the setting, and perverse sheaves on the nilpotent cone kind of fit into this broader context. So the next slide is about this context. So roughly the first half of my talk was in this setting, and Springer theory with rational coefficients was initiated by Springer in the 1970s before the invention of perverse sheaves. So he formulated in a slightly different language, which you can reinterpret in perverse sheaf language. And I think that reinterpretation is due to Lusztig and Borho McPherson. And Springer's original Springer correspondence related representations of the Weil group to some of these local systems on nilpotent orbits, but not all of them. And then in 1984, in 1984, as part of his work on character sheaves, Lusztig produced what's now known as the generalized Springer correspondence. And then on the positive characteristic side, the story began in 2007 with Daniel Juteau's thesis. And then myself and three other people over the course of a few years, we wrote a series of papers where we proved a statement similar to Lustig's in the positive characteristic setting. So the main result is something like a classification of irreducible objects in this category of perverse sheaves via representations of groups that look like this. So it's a normalizer of a Levy model Levy. So this could be a Weil group, but it could be other Levies also appear. So something like a relative Weil group. But well, we proved a theorem that there is some bijection. Lustig's work, like in the same paper, well, not the same paper, but like in another paper published 3 months after the first one, he also gave this algorithm for computing stalks, which I already mentioned and is a crucial part of the character theory of finite groups of Lie type. In the modular world, computing anything is sort of impossible. Even before you get to computing stalks, you could say, well, you know, what is this classification? Like when I say classify, well, there's a bijection between one thing and another thing, but can you write down what the bijection is? And so even writing down the bijection is not known in all cases. So writing down the bijection is hard. And in our papers, we did it in some easy cases. So some easy cases. And just recently, my student, Joseph Dorta, did it for the symplectic group in general. And hopefully his methods will make the other classical groups able to be tackled. But I mean, for the exceptional groups, I have sort of no idea how to start these computations. Yeah, equivariant perverse sheaves. Yeah. 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 So what do we do about this? So about 10 years ago, Karl Mautner, who's one of the inventors of the theory of parity sheaves, proposed an idea that, his vision was that this idea would allow you to reorganize all the Springer theory in a way that makes it more amenable to computations. And, in Lusztig's setup, cleanness was, a crucial foundational feature of the theory. And so Mautner's idea was that if cleanness holds in the modular setting, maybe we can exploit it in a similar way. So his precise conjecture is this. So you start with a nilpotent orbit, and you take a cuspidal local system, but a rational one. So with characteristic zero coefficients. And then there's a constraint on the prime characteristic that I'm gonna go to. And rather good, it's some technical condition, and it's pretty mild. And I'll say more about that in a second. But what you do is you take like an integral form of your local system, and then you reduce mod L. And Mautner's conjecture is that this remains clean. And it's definitely false if L is not rather good. And I can give you a counterexample right away. The counterexample for G equals SL2 and L equals 2 is this. So this, this is the picture we had. So here's C reg. So the observation is that the cohomology of C2 minus 0 with FL coefficients equal, so this, remember, this is the same as the cohomology of the three sphere. And I want this to be the same as the cohomology of C reg with FL coefficients. And this, remember, is homotopy equivalent to RP3. Well, this is true if L is different from 2, and it's false if L equals 2. And this false thing means that the integral version of the sign representation tensored with F2 is not clean. So this comes down to an algebraic topology calculation about real projective space.
So you have example that the integral form is unique, but in general, does that depend on the integral form?
No, it turns out it doesn't depend. I mean, whether this is clean or not is independent of the integral form you choose. So if it's clean for one of them, then it's automatically clean for all of them. Okay, so let me tell you a little bit about the history of this cleanness conjecture. So in 2013, so around the time Mautner was formulating his conjecture, well, he didn't formulate it in a vacuum. He had computed some examples, and it turns out that it's quite easy in type A. They're for sort of roughly because the group SLN has a big center that helps you do the computation in an easy way. So it turns out to be easy in type A. It turns out that, Mautner also checked it in types B4 and C3.
Type A is true.
The type A is true, yeah.
And what is that?
Is
it the order of the white group?
No, so the bound on the prime actually depends on which group you take. So for SLN, you need the prime to be you need N to not be divisible by P. But for GLN, all primes are okay. So if you have something sort of like if you take SLN mod a central subgroup, then there's some other set of primes that you have to worry about. But SLN is kind of the worst one.
So then we should not divide N as factorial.
It should not divide. It should not divide N. Yeah, it should not divide N. Yeah. Right. For GLN, the fundamental groups of all nilpotent, the equivariant fundamental groups of nilpotent orbits are trivial, and all primes are rather good for GLN. Okay. So I'll also have a comp for what I thought at the time. And type A is easy, but B4 and C3, Carl explained his computations to me, and I was like, I can't do that computation. That's too hard. Like SL2 is all I can do. Then in 2015, as part of this work with Henderson, Juto, and Reich, we did check it in a few more cases, D5 and the exceptional groups. But this was by a trick. This trick used the full power of the modulo generalized Fourier correspondence. It was not a hands-on sheaf theory calculation of the kind that I did at the beginning of the talk. So here I thought this gives me no insight.
So all
the exceptional groups, yeah. The trick there is that rather good primes don't happen not to divide the order of the Weil group. So that simplifies things a lot. Okay, then in 2019, my student, Tamanna Chatterjee, her thesis was about something else, but in the course of working on her thesis, she also did some of these cleanness computations, and she did a few more cases in type C. So she did some computations in, well, SP6, I guess SP6 is C3, so I think she redid Carl's computation in a way that, well, she explained it to me, and that time I followed it. And she also did SP8. And, when you're trying to prove something is clean, you want to show something is 0. And what happens is that you'll do intermediate calculations where you get something non-zero, and you need things to cancel. So when Tamana did these calculations, it seemed like maybe there's a pattern to how they're canceling. So if you do a little bit more, we could make precise the pattern, and then we'll have something to try to prove. And then she went on and she wrote a thesis on something else. But then in 2021, she was here at she just started as a postdoc here at UGA, and we were talking. We're like, well, let's look at this again. And she computed SP10, and the cancellation did not work the same way. And so my feeling was despair. And then in 2022, yeah, so we couldn't get this cancellation to work, but we still set up a kind of outline of a paper where we kind of we kind of tried to pin down the part we didn't know to as small a piece as possible. So there are some cohomology calculations, and we need to know that some part of it is 0. And then, like, we have the rest of it in our argument sort of in place to prove a parity vanishing statement and various other things. And then we're kind of stuck that way for a year and a half, and we're like trying to come up with ways where it makes, like, how can we complete this paper? Like, we need to write something. And then in September of 2023, we had a breakthrough. So yeah, so what's hard about, but I mean, the kind of thing you see in all of these things is that you know, you want some cancellation to occur, so you get 0 as the answer to something, and if some of the intermediate calculations vanish in odd degrees, that's most of the work. Then you get a lot of cancellation for free. But you end up seeing things like cohomology of a quadric. And typically these things just honestly do have cohomology in odd degrees. It's not 0. And so the problem is to package up all the complicated quadrics you don't like in a way that they cancel before you have to see what they are. And so this works. And so the theorem is that Mautner's cleanness conjecture is true in general, and also that there's a parity vanishing property for induction in this setting. So this is proved by induction on semi-simple rank. So the pattern of the proof here. So I copied this other thing from these theorems of Lusztig from earlier in the talk. The pattern of the proof for these two statements is structurally very similar to the pattern of Lusztig's proof, but of course the details are very different. And now that this is done, I mean, this is just the first step of hopefully being able to do more. You know, for Lusztig, this is the first step of getting to the Lusztig-Chatterjee algorithm and having an algorithm for computing characters of finite groups of Lie type. So hopefully this work can pave the way to making some of this modulo Springer theory stuff more computable. Okay, so I'll stop there.
Is the proof uniform or is it still case by case?
Yeah, the question is the proof uniform or is it still case by case? And it's case by case. It's yeah.
And prime, you know the optimal prime where it is true.
Yeah. So basically, like type A was done and the exceptional groups were done. So it's left. I mean, the new content of Mautner's cleanness conjecture is only for the classical groups, and rather good for the. I mean, classical not including type A. And for those groups, rather good means not 2. So for all primes other than 2, the conjecture is true. And yeah, I mean it's definitely case by case. It's I mean there's kind of it's an intertwined, like you some have to do the symplectic group and the orthogonal group together because they each occur as parts of centralizers of nilpotent elements in the other group. So they're kind of intermeshed that way. So in this induction, you have to do both of them simultaneously.
Does it make sense to extend from reductive groups to supergroups?
The question was, does it make sense to extend from reductive groups to supergroups? And I have no idea.
Said from Lusztig's work. I can't quite remember now anymore, but in Lusztig's original work, there was some connection. This corollary said that cleanness was essentially the same as cuspidal.
Yeah, that's a good question. I mean, is it true in this modulo case that that a local system is clean if and only if it's cuspidal? My guess is yes, but I don't. I mean, at the stage in Lusztig's work where you find this out, you already kind of know a lot more about. I mean, you can. I mean, the statement there that clean is equivalent to cuspidal. It's because you have an algorithm for computing the stalks of everything, and you can just check that this algorithm is guaranteed to give you non-zero output on a non-cuspidal. And so my guess is that that is true in the modulo setting as well, but the machinery isn't there at the moment to try and prove it the same way. And I don't know if there's another proof that'd be possible. So.
Okay, let's thank Mr. again.